Hey there, welcome to the recorded presentation on logarithms and exponentials. My name is Aaron McDonald and I'll be your guide through the presentation today. Let's go ahead and talk about what we're going to cover in the presentation. The first key concept is exponential notation and thinking about integers as exponents and dealing with them when they show up in exponential notation. Once we're done with that, we'll begin discussing the relationship between logarithms and exponentials and learn how to convert between the two notations, logarithm notation and exponential notation. Once we have the converting down, we'll be ready to start calculating logarithms because we can use our skills with exponentials to solve logarithm problems once we know how to do that conversion. So we'll follow it up at the very end with calculating different logarithm problems. By the end of this presentation, I hope you're both comfortable and excited about logarithms because they're not really as nebulous and scary as they look at first glance. So let's go ahead and get started. Exponentials are simply shorthand notation for repeated multiplication of a number or a quantity in the case that you're working in algebra. We'll stick basically just with repeated multiplication of numbers in this presentation, but know that this concept extends over into algebra as well when you're working with a general quantity like x. So, as I said a moment ago, exponentials are simply shorthand notation for repeated multiplication. I have some examples here on the screen for you, and the first two involve repeated multiplication of a number. In the first example here, we're looking at repeated multiplication of the number 2. I'm multiplying it together 1, 2, 3, 4, 5, 6 different times. So instead of writing 2 times 2 times 2 times 2 times 2 times 2 like I have here in brute force across the screen, mathematicians have developed a notation called exponential notation, and this would be the notation I would use to represent 2 being multiplied together 6 times. It's a 2 with a 6 in the superscript up here. A 2 with a superscript 6. 2 with a superscript 6. And the way that I read this is 2 to the 6th power. 2 to the 6th power. 2 means it basically tells you the number that's being multiplied, and the power up here, the superscript, tells you how many times to multiply it together. So 2 to the 6th power is simply 2 times 2 times 2 times 2 times 2 times 2 when we write it out, and when we do that multiplication we get 64. Well, we can do this kind of repeated multiplication with a negative number as well. Here we are going to take the number negative 3 and we're going to multiply it together 4 times. So I'm looking at negative 3 raised to the 4th power, or negative 3 to the 4th power, which is negative 3 times negative 3 times negative 3 times negative 3. I'm taking that negative 3 and multiplying it together 4 times. And when I do that multiplication, I get 81. Keep in mind that you need to be very careful when working with negative numbers when you're dealing with exponentials, because the sign may be positive or negative. The solution may be positive or negative. So be careful when working with those negatives because I know they can be tricky at times. Again, we can extend this idea over into algebra by looking at x to the 5th power, x raised to the 5th power, which simply means to take the number, quote, x, whatever it is, and multiply it together 5 times. So it's x times x times x times x times x. And again, there's not much we can do with this until we're actually given a number for x that we can plug in, and then we can do the computation, we can do that multiplication. But for now, the best we can do is write x to the 5th power, or simply write the multiplication out literally. Exponentials are just shorthand notation for repeated multiplication. In that conversation, you probably heard me use some of the key vocabulary for exponential. So let's go ahead and go over it here on this slide to make sure that it sticks. Remember, here is an exponential, and the exponential has 2 parts to it. The part that tells you the number that's being multiplied together a certain number of times, and a part that tells you how many times to multiply the number together. The number that's being multiplied is called the base of the exponential. So in this case, 2 is the base and 2 is the number we're multiplying together. I know you heard me say this earlier. The power is the superscript number, which tells me how many times to multiply the number 2 together, or in this case, the base together. So the power of the exponential tells tells me how many times to multiply the base together. So once we've done that multiplication, this would be 2 times 2 times 2 times 2 times 2 times 2, which turns out to be 64. You can do it by hand or using your calculator. We can write the statement 2 to the 6th power is equal to 64. And that number 64 is the solution of the exponential. It's the number that you compute when you actually do the multiplication that the exponential represents. So we have the base of the exponential, the number that's being multiplied together, the power of the exponential, the number of times you multiply the base together, and the solution of the exponential, which is the result when you actually do the multiplication. It's the result of the mathematics. Base, power, and solution. Important to keep in mind. So how do you handle exponentials when you're given a negative power? Remember, the power is a little superscript number that tells you the number of times that you're supposed to multiply the base together. How do I multiply 2 together -1 times? That doesn't make sense. How do I take 2 and multiply together -4 times? That doesn't make sense either. So let me explain to you what negative powers mean, or integer powers mean. Essentially what it means is it's kind of another shorthand notation or concept to remember, but it tells you that you're going to take the base and work with its reciprocal. You're going to work with its reciprocal instead of the base itself. So for instance, this little negative sign here tells me I'm going to be working with the reciprocal of 2. Remember, this reciprocal is the number you get when you flip a fraction upside down. And we can think of the number 2 as the fraction 2 divided by 1, or 2 over 1. So if we flip 2 over 1 upside down, we get 1/2. Okay, so the little negative sign when you're working with exponentials tells you that you're working with the reciprocal of the base, or the fraction turned upside down. So we'll be working with the number 1/2 for this particular example. Now the actual digit part of the integer, so the 1 here, tells you the number of times that you're going to multiply the reciprocal together. So negative means use the reciprocal, the 1 means you're only multiplying it together 1 time. So the answer is just 1/2, which we could write as a fraction, or we could even write it as a decimal. We could convert that over to decimal notation to get 0.5. Well, what about 2 to the -4th power? 2 to the -4th power would be asking you to work with a reciprocal of 2 because of the negative sign, which is 1/2, and we're going to multiply that reciprocal together 4 times. 1/2 times 1/2 times 1/2 times 1/2, and there it is. The answer here is 1/16, but where did that come from, you might be wondering. Remember, when we're multiplying fractions, we just multiply all the top numbers in a row. So 1 times 1 times 1 times 1 gives me 1 for the top. And then we multiply all the bottom numbers, 2 times 2 times 2 times 2, which gives me 16 for the bottom. So 1/16 is the solution for the exponential 2 to the -4th power. And we can plug that into our calculator and convert it over to decimal notation. The decimal representation is 0.0625, and this would be the exact decimal representation. There's no rounding that occurred there. Alright, let's look at one last example. Powers of 10 are actually super important to the way our number system is built and the way we use numbers every day. So knowing your powers of 10 is a big deal. Both positive powers and negative powers. So let's think about a negative power here, 10 to the -3rd power. What do we do with that? Well, the negative in the power tells me, again, I'm working with the reciprocal of 10, which is 1/10, and I'm going to multiply together 3 times. So I have 1/10 times 1/10 times 1/10. Again, using the multiplication of fractions thought process or algorithm, we get 1 times 1 times 1 for the top. And we get 10 times 10, which is 100, times 10 again, which is 1,000 for the bottom. So we get 1/1000th as the fraction. That is the solution of 10 to the -3rd power. If we convert this over to decimal notation, we get 0.001. Notice that we are looking at the 1 being 1, 2, 3 places to 1, 2, 3 places to the right of the decimal, which corresponds very nicely to the -3. Okay, you can do some more exploration with the powers of 10 to see how the powers of 10 are related to positions of the decimal here. Regardless, keep in mind negative powers of 10 are important it's a form of exponential notation. We're definitely going to use the reciprocal of 10, which is 1/10 when working with the negative powers. We multiply it together to get the fraction as a solution, or we can convert it to a decimal as well. Either or is fine. Alright, so hopefully you have an idea of what an exponential is, and you have a fairly good idea of what an exponential is when it has a negative integer for its power. Let's now talk about logarithms. Logarithms are just an alternative way to write an exponential. So I've shown you four different logarithms here, and I'll read them for you so you can start to learn the language of the logarithm. It says log base 3 of the number 9 is equal to 2. So log base 3 of 9 apparently is equal to 2. Log base 5 of 125 is equal to 3. Log base 2 of the number 32 is equal to 5. And log base 4 of the number 64 is equal to 3. Okay, now I promise you for each of these log problems you can just work with the three numbers that you see in it and use those three numbers to write exponential notation. And you can even write a true statement. You can form an exponential and set it equal to its solution using those three numbers. Let me show you what I mean by that. Let me get my little pencil ready here. Okay. Here we go. Alright, so here we go. Log base 3 of 9 is equal to 2. So what I'm saying is we can take these three numbers and start to form different exponentials with them. Like we could do 3 to the 9th power. That's working with two of the numbers, 3 to the 9th power. Or opposite, we could do 9 to the 3rd power. Or we could start to involve the 2. We could do 2 to the 9th power. Or we could do 9 to the 2nd power. Or we could do 2 to the 3rd power. Or we could do 3 to the 2nd power. There's all kinds of exponentials we can form using these numbers. So what I'm saying is you can use two of the three numbers to form an exponential, and the third number freakishly turns out to be the solution of that exponential. So for instance, one guess might be to form the exponential 3 to the 9th and then ask, is 3 to the 9th power really equal to 2? I doubt that's the case because this is 3 times 3 times 3 times 3. There's four of them. 5, 6, 7, 8, 9. Is that multiplication, when we do it all out, is there any way that that can be equal to 2? Absolutely not. This is going to be a really large number. I know 3 times 3 is 9 times 3 again is 27 times 3 again is 81 times 3 again. It's going to be really big. It's certainly not going to be 2. So I know that's not the right exponential expression. It's not the right exponential relationship to this logarithm. So what about 9 to the 3rd power? Is 9 to the 3rd power equal to 2? If we form this exponential, is it equal to the number that's left over, which is 2? No. 9 to the 3rd power is a big number as well. This is 81 times 9, so that can't be it. 2 to the 9th power, again, that's taking 2 and multiplying it together tons of times, 9 times actually. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. Is there any way that that can be can be equal to the number that's left over, which is 3 in this case? Is that equal to 3? No way. We know that's not the case. 9 to the 2nd power, that's 9 times 9, that's 81. So there's no way that can be equal to 3 because I know it's 81. 2 to the 3rd power, that's 2 times 2 times 2, which is 8. So 2 to the 3rd power, the number that's left over is 9. So that's close. At least 2 times 2 times 2 is close to the number that's left. The number that's left over is 9. We know this is 8, so it's not true, but it's close. We're getting closer. What about 3 squared? That's the way we sometimes say 3 to the 2nd power, 3 squared. 3 times 3, that is 9. That certainly is the number that's left over. So this logarithm, log base 3 of 9 equal to 2, has an equivalent exponential expression that's 3 squared equals 9. It's a true statement that we can write that involves an exponential using only the numbers that we see in the logarithm. So let's try it again. Logarithm. Here's the three numbers, 5, 125, and 3. What exponential expression can we write using these three numbers that is itself a true statement? I know I'm probably not going to want 5 to the 125th power because that's going to be a humongous number. 125 to the 5th power, for instance, it's going to be big too, because we're taking 125 and multiplying it together 5 times. There's no way that's going to be 3. So you can start to play around with these to gain some intuition, but I'm thinking that you're probably going to be guessing it's going to be 5 to the 3rd power is equal to 125, or 3 to the 5th power is equal to 125. So which of those is true? 3 to the 5th power is 3 times 3 times 3 times 3 times 3. So let's grab our calculator and see if that works. 3 times 3 times 3 times 3 times 3. That's 243. So that one's not correct. This is not a true statement. So let's see if this one is. This is 5 times 5 times 5. So 5 times 5 times 5 is 125. That is true. So there's our relationship. 5 to the 3rd power equals 125. And as you look at this next one, you'll see that we're working with the numbers 2, 32, and 5. Once you've played around with it a little bit, you'll see that 2 to the 5th power is indeed 32. And the last one here, you'll see that 4 to the 3rd power is equal to 64. And you're probably wondering how I'm doing these so quickly. There's a pattern to what we've just been doing. As we were playing around with these numbers, the same numbers took on the same roles in each case. So for instance, this number here, whatever it is in the logarithm, always turns out to be the base of the exponential. Those are the bases. So the base of the logarithm turned out to be the base of the exponential as well. The base of this logarithm, base of the exponential. Base of the logarithm, base of the exponential. Base of the logarithm, base of the exponential. Also notice that the solution of the logarithm over here turned out to be the powers. Solution of the logarithm, power of the exponential. Solution of the logarithm, oops, here's the solution of the logarithm, power of the exponential. Solution of the logarithm, power of the exponential. And of course, the number that's in the middle of all of this madness turns out to be the solution for the exponential in each case. So there's a very nice relationship between logarithms and exponentials. The base of the exponential is always the base of the, the base of the logarithm is always the base of the exponential. The solution of the logarithm is always the power of the exponential. And the number that you're working with in the logarithm is going to be the solution of the exponential. So the language of the logarithm, log base 3 of the number 9 is equal to 2, could be thought of in a different way. This is log of 3, log base 3 of the number 9 is equal to 2. We can automatically look at this and think in our head, I don't like logarithms. So I'm going to think of this as I'm looking at an exponential with base 3 raised to the power 2, and I know that that's equal to 9. Base of the exponential is 3 raised to the power 2. That's 3 times 3. I know that answer is 9. So we can start to think about these logarithms in terms of their exponential counterparts. And that might help us grow in comfort with logarithms. In fact, I know it will. So let's talk about the relationship again. Anytime that you're looking at a logarithm, you can convert it to an exponential. Remember, whatever the base of the logarithm is, it becomes the base of the exponential. And whatever the solution of the logarithm is, it becomes the power of the exponential. And lastly, whatever number you're trying to take the logarithm of, it becomes the solution of the exponential. So you can take any logarithm and automatically convert it into an exponential. And we understand what exponential notation means. It is repeated multiplication of the base. Here, the number b, whatever it is. So, for instance, log base 2 of 32 equal to 5. I don't like the logarithm, so I'm automatically going to rewrite it as its exponential counterpart. I'm looking at a base 2, I'm looking at a power 5, and I know that that is 32 if I multiply it out. So there it is, its exponential counterpart. Same with this, log base 6 of 216 is equal to 3. Don't like it, so I'm going to rewrite it as its exponential counterpart. I'm looking at base 6, I'm looking at a power 3, and I'm looking at a solution of that exponential of 216. Lastly, this would be 10 raised to the second power is equal to 100. We can also do it when we're working with decimals or fractions. Doesn't matter. So what this is telling me is I'm looking again at a base of 4, a power of -3. Aha, it's starting to make sense. Remember, this means that we're going to take the reciprocal of 4 and multiply it together 3 times. Remember, all those answers turned out to be fractions or decimals. So this is telling me that the answer is going to be 0.015625 without having to do that fraction math. How cool is that? So we could take these logarithms and automatically convert them into exponentials. Super cool. So let's go ahead and continue practicing that. Let's write each logarithm that's given to us here as an exponential. Wow, this wasn't very interesting because I just chose a problem that we looked at a moment ago. Remember, this is log base 10 of 100 equals 2. The base of the logarithm is always the base of the exponential. And the solution of the logarithm is always the power of the exponential. And the number that you're taking the logarithm of turns out to be the solution of the exponential. So we can put those pieces together and form our true statement, which involves the exponential 10 to the second power is equal to 100. All right, let's continue on. What about this one here? We're looking at base 3. So base 3. And, oh wow, I think there's a mistake here. What do you think? This would be base 3 raised to the 243rd power is equal to 5. Is that true? No, I made a mistake. The logarithm, this is not a true logarithm statement. The logarithm should read log base 3 of 243 is equal to 5. So that the correct exponential relationship would be 3 to the 5th power equals 243. And let's go ahead and check that just to make sure. Remember, this is 3 times 3 times 3 times 3 times 3. So bust out your calculators. Let's do 3 times 3 times 3 times 3 times 3. That is 243. Cool. So I had the wrong problem here. I apologize for that. So the problem should have read log base 3 of the number 243 is equal to 5, and the correct conversion to exponential is 3 to the 5th power equals 243. Okay, let's do another example here that involves a negative power and a decimal. We're looking at base 2 to the -3 power is equal to 0.125. And again, we can check this again if you want. We're taking 1/2 and multiplying it together 3 times. 1 times 1 times 1 is 1 on top. 2 times 2 times 2 is 8 on the bottom. When I plug that into my calculator, 1 divided by 8, I get 0.125. Super cool. Alright, so I encourage you to continue practicing converting logarithms to exponentials. The logarithm may not make a lot of sense to you unless you view it through the lens of an exponential, or said another way, unless you rewrite it as an exponential. And the reason I say that is because exponentials are very intuitive. They're easy to understand, and it just involves multiplication. We're multiplying a single number a certain number of times. Well, we can always work backwards, meaning I can give you an exponential and you can write the logarithm. It's very unusual to move in this way from an exponential to a logarithm, but in certain circumstances it might be advantageous. We won't talk about those circumstances, but it's good to know how to do this just in case you arrive at one of those places in the future. Remember, the base of the exponential is always the base of the logarithm. The two expressions, the exponential expression and logarithm expression, always share the same base. So we have log base 4, always goes there. And remember, the power of the exponential is always the solution of the log. It's the number that's over here on the right hand side of the logarithm. So I'm looking at log base 4, and the number that's left over is 64. Log base 4 of 64 is equal to 3. Let's try another one. Remember, the base of the logarithm is the base of the exponential. The base of the exponential is the base of the logarithm. So I'm looking at log base 7 in this case. And the power here always goes on the right hand side of the logarithm. And I'm left with 49 to go into the middle spot, which is the number I'm trying to take the logarithm of. So log base 7 of the number 49 is equal to 2. The last example we'll do here is a log that involves log base 10. Just as it's important to know the powers of 10, it's kind of important to know the logarithms that involve log base 10. They're actually probably one of the most useful logarithms that we know about. There's another one called log base e that we'll talk about another time, but log base 10 is super important. You might even see a button on your calculator that involves log base 10. So how do we continue to convert this? So the base of the exponential is the base of the logarithm. Then the power of the exponential becomes the right-hand side, or the solution of the logarithm, and whatever's left over goes in the middle. So the decimal goes in the middle here. So log base 10 of the number 0.01 is -2. Alright, so it's kind of important to know how to convert backwards from exponential to logarithm. It's not a trick we'll use very often, but certainly good to know. The relationship goes both ways. That's the moral of the story. So let's move on now to calculating logarithms. Remember I said once we get through the relationship between exponentials and logarithms and develop a comfort for logarithms, we'll know how to do comfort for exponentials. We'll know how to do logarithms without too much of a problem. So let's give it a whirl. Let's see if I was lying to you or if you believe me now. So we're going to try to calculate log base 8 of 64. I have no idea what log base 8 of 64 is. Even if I tried to pick up my calculator, it couldn't do it for me. So we need to remember how to solve this problem using exponentials. So let me show you how to do it. So really what we're after is finding what value is equal to log base 8 of 64. Or if I tried to calculate log base 8 of 64, what number would it equal? So sometimes we might put a question mark there. More formally, we usually write x when it's a number that we don't know. Question mark or x doesn't matter to me, whatever you feel more comfortable with, perfectly okay. We're trying to figure out the answer to this problem. Log base 8 of 64 is equal to what number? Or log base 8 of 64 is equal to x. X again just represents the idea of what number is that? Okay, so what do we do with that now? So let's take these expressions. I'm going to work with this one, and let's convert it to an exponential. This is a logarithmic expression that we can convert to an exponential expression. So here we have the base of the logarithm's 8, so the base of the exponential is going to be 8. X, the number over here on the right hand side, is going to be the power of my exponential. It's okay that it's a variable. We just don't know what it is yet. And 64 is going to be the solution of the exponential. That's how they're related. That's how they roll. So we have 8 to the x power equals 64. Now, why does that matter? Why is that helpful? This asks a very pointed question that you can solve just using some of your number skills. It's asking you what power of 8 is equal to 64. Apparently one of the powers of 8 to the first power, 8 to the second power, 8 to the third power, 8 to the fourth power, and so on. One of those powers is equal to 64. Which one is it? So it just becomes a matter of looking at the powers of 8 and figuring out which one is the right answer. Is it the first power? Is it the second power? Is it the third power? Is it the fourth power? Which one is it? Well, 8 to the first power is just 8. I know that's not the right answer. 8 to the second power is 8 times 8, and that is 64. So I know the power that solves this problem is 2. The secret number for x is 2. It's the second power of 8 that is equal to 64. So the power is 2 because 8 squared is equal to 64. So I have just discovered that the secret number x is really the number 2. Okay, I used exponentials to figure it out. And now all I'm going to do is go back to my logarithm and say log base 8 of 64 is equal to x. Hey, wait a second. I know what x is. X is 2. I figured it out. So the solution to log base 8 of 64 is 2. Log base 8 of 64 is the number 2. Cool. Let's keep practicing. So log base 11 of 1331 is equal to what number? What is it? We don't know what it is. We can't even use our calculator to figure it out. So we're going to have to use our tricks that we've just learned to figure it out. So we're going to convert it to an exponential. So we have our statement here. We'll convert to an exponential. The base of the logarithm is the base of the exponential. Here's my power, and I'm going to set it equal to 1331. And now this asks a very pointed question. What power of the base 11, so what power of 11 is 1331. Okay, so let's start looking at the powers. 11 to the first power, 11 to the second power, 11 to the third power, 11 to the fourth power. Got any guesses for me? I don't even know what it is. I don't know my powers of 11 that well. I know it's not the first power because 11 to the first power is 11, which isn't the right answer. And I'm pretty sure it's not the second power because I think that's 121. Yeah, that's right. So this is 11 times 11, which is 121. That's not the right answer. What about 11 times 11 times 11? Ah, there it is. There's the magic power. 11 times 11 times 11 is 1331. So the magic power is 3. So the answer to the problem is 3. There we go. Log base 11 of 1331 is 3. It's kind of fun, huh? Once you know how to use exponentials to help you solve the problem. Let's keep going, okay? Doesn't matter if we're working with fractions, decimals, whole numbers, integers, we can figure it out, right? All we need to remember is the logarithm trick. Convert it to an exponential. So we don't know what it is. As I look at this fraction 2, I could write it as a decimal if I feel more comfortable with that. So it could be log base 10 of 0.01 equals x. Either one of these, doesn't matter which route you go. If you like fractions, definitely work with what's given to us. If you prefer decimals, go ahead and convert this fraction 1 over 100 to a decimal so that you're looking at log base 10 of the number 0.01 and trying to figure out what it's equal to. Regardless of which way you go, you will get 10 to the x equals 1 over 100, or you'll get 10 to the x equals 0.01. There's one reason why I wanted to show you the decimal way over here to do it, because when we were working with our negative powers, remember those, like 2 to the negative 1 power, 2 to the negative 4 power, 10 to the negative 3 power? In each case, the answer was a proper fraction, ding, 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 or it was a decimal, ding, 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 ding. So anytime that you form an exponential like this and you see the solution of the exponential is a proper fraction, or you see the solution of the exponential is a decimal, that is a clue. That is a great clue that you're going to be studying the negative powers of 10. So remember, we're asking what power of 10 is 1 over 100, which is equal to 0.01. What power of 10 is that? It's not the positive powers of 10. You could try problem solving that way, but you'd learn really quickly that this is not leading you towards a solution. The first power is 10, the second power is 100, the third power is 1,000. These numbers are nowhere close to this decimal 0.01. So the negative powers are where the action's at this time. So remember, this is 1/10. 10 to the negative power, it means work with the reciprocal of 10, which is 1/10, and just have it one time. So I'm going to convert that to a decimal. 1 divided by 10 is 0.1. So that's not the right answer. So this is going to be 1/10 times 1/10, which is 1 times 1 is 1, 10 times 10 is 100. Convert that to a decimal, and oh my gosh, there it is, 0.01. There's what we're looking for, right? That's what we're looking for. So in this case, the magic power is -2. So the answer to our problem is -2. So again, as you're working with fractions or as you're working with decimals in the either in the logarithm spot, you're taking the log of a decimal or the log of a fraction, or when you're looking at an exponential expression where the right hand side involves a fraction or a decimal, you're going to be working with negative powers. So keep that in the back of your mind because it might lead you to the solution a little bit faster. Alright, let's try another one. Here's log base 2 of the decimal 0.0625. Here's another example where we're trying to take the log of a decimal. As I convert that to exponential notation, I notice I have that decimal over here on the right hand side as a solution. Again, another great tip. Another great, yeah, it really is a tip. It's a great tip. If this is a decimal, if the right hand side is a decimal, just start working with the negative powers. Don't even bother with the positive powers because they'll lead to big whole numbers, and we're looking for decimals. So 2 to the negative first power is 1/2, which is 0.5. I have that one memorized. 2 to the negative 2 power is 1/2 times 1/2. And I do my fraction multiplication. I get 1 on top, 4 on the bottom. That's 0.25, right? 1/4 is equal to 25 cents, a quarter. That's not what I'm looking for, so let's try 2 to the 3rd power, see if that works. So that's going to be 1/2 times 1/2 times 1/2. We do that multiplication, 1 times 1 times 1 on top, 2 times 2 times 2 on the bottom, which is 8. Oh, I don't know that one offhand, so I'm plugging that into my calculator. I get 0.125. I think we saw that one earlier. So that's not it even. Maybe 4. Negative 4 is the magic power. 1/2 times 1/2 times 1/2 times 1/2. 1 times 1 times 1 times 1 gives me 1 on top. That's super easy. 2 times 2 is 4. Times 2 again is 8. Times 2 again is 16. So I'm looking at 1/16, which I have no idea what that is. Plug it into my calculator. Look what I get, 0.0625, what I was looking for. So that means the magic power that I was looking for is negative 4. So the answer to this problem is negative 4. Cool. All right, let's look at one that's a little bit more tricky. So you might be tricked into thinking that this one is going to be a problem where the solution is going to be a negative number again, but look at the difference here between what we have here and what we had previously. So let me scroll back so you can see it. Here we were working with a proper fraction, 1 over 100. Proper means that the number on top is smaller than the number on the bottom, 1/100th. And here we are working with a decimal. It's definitely less than 1. Here we're working with a fraction that's not a proper fraction. As a matter of fact, this is just trying to be sneaky, because 27/9 is just 3. So why not just rewrite that as 27 over 9, which is 3. And so what we're looking at here is 3 raised to what power is 3. Okay, this is a whole number now. It started as a fraction, but there was no reason for it to be rewritten that way except to be sneaky. So 27 divided by 9 is just 3. So we're looking at 3 to the x power is equal to 3. Powers of 3, we don't have to go very far because 3 to the 1st power is 3. So I know that the secret number I'm looking for here, the magic power, is 1. So the answer is 1. So this is a case where the answer is positive. So it's not just that there's a fraction there, it's that it's a proper fraction, you'll get a negative answer. If it's not a proper fraction like this, you're going to get a positive answer. Cool, so hopefully this was helpful to you as you work in the module on exponentials and logarithms, and you're starting to gain a better feeling about logarithms. They really originate from exponentials, and exponentials aren't as scary as you probably thought they were at first. So hopefully if the exponentials aren't scary, neither are the logarithms. Well, you have the full support of the QLC1 course mentoring team. They're a wonderful group of teachers, and they're happy to work with students who are struggling with any concept. It could be exponentials, it could be logarithms, it could be something else. Feel free to reach out to them to talk with them about your questions and your concerns. They'll make more than enough time for you. They love working with students. Reach them by email at ql@wgu.edu. You can reach them by phone. There's one phone line that reaches out to all the mentors at once and connects you with the mentor that's available. That toll-free number is 1-866-895-9660, extension 1758. And lastly, the mentors host various chats throughout the week where you can come to a virtual classroom, learn a concept, ask your questions, engage with the mentor, engage with your students, learn from each other. It's really, really helpful, synergistic environment. Click on the live QLC1 chat button in QLC1 My Math Lab to see a list of the chats that are available to you this week, and also the information you need to log into that chat. Again, thank you so much for joining me today to talk about logarithms and exponentials. We'll talk to you soon.